Alrighty, let me show you how to get into frequency domain. What you're seeing here is a 10 megahertz 5 volts peak-to-peak signal on channel 1. And what I'm going to do is select math and F1. And it's already set up for frequency, but what that means is function 1, and if you go down to the function, you can choose the source, which I've selected C1, and FFT. Okay? So that's pretty much all there is to it. You'll notice frequency across the bottom and volts across the top. You need to set it up to center your 10 megahertz frequency. So if you hit math again and you go to horizontal, you're going to need to change a couple of things in here. You want to put your signal at the center of the screen, and so if you hit this center twice, I'm going to enter 10 megahertz. And then you need to say that the span is twice that. So I hit that twice and I say 20 megahertz, and then I want to start at 0 hertz and go to 20 megahertz. Now if you start changing the horizontal counterclockwise, you'll see a very nice peak for 10 megahertz right in the center of the screen. And one of the things you're asked to do, it's a different frequency than this, but you need to do a screenshot of both the real-time and the frequency domain spike for the lab, and I think it's 1 megahertz instead of 10 megahertz. To demonstrate alias, what we're going to do is change its sampling frequency. Alright, you can see right here it's 2 gigasamples per second. If I take the horizontal knob and I start changing that counterclockwise, eventually you're going to see the sample rate drop. Here's 1 gigahertz, 400 megahertz, 200 megahertz, and I'm going to go on down to 20 megahertz. Okay, at a 20 megahertz sampling frequency, the Nyquist frequency is 10 megahertz. Once you do that, go back to math and make sure that your center is still at 10 megahertz. Okay, because it will probably change. All right, 10 megahertz, the span is 20 megahertz, start at 0 and end at 20. And if you're set up correctly for a 10 megahertz signal, you'll just see the little bit of the spike for 10 megahertz right in the window. I'm going to reduce the frequency from 10 megahertz to 8 megahertz, and you can see the peak shift to the left. But what you're going to do is document what happens to generate an alias signal, and that happens when the frequency content of your signal exceeds the Nyquist criteria for sampling. Our Nyquist frequency is 10 megahertz. Let me go to 9 megahertz. Here's 10 megahertz again, and at 11 megahertz something interesting happens. Instead of getting 11, let me go to 12 megahertz. Instead of getting 12 megahertz, it folds back and you get a frequency spike in the digital data of 8 megahertz. And on a digital display, you will actually see 8 megahertz. If I were to change the settings on the scope, it's going to change the sampling frequencies. This is why your Nyquist frequency is also called the folding frequency, is once your signal hits that Nyquist frequency, it's going to get folded back in frequency by exactly the amount of how far it exceeds the Nyquist frequency. I'm at 12 megahertz, it has exceeded the Nyquist frequency by 2 megahertz, and so it folds back from 10 megahertz by 2 megahertz, and you end up with all the energy at 8 megahertz. Okay, it's very difficult to see that as a standing wave. I can tell you that the 8 megahertz is definitely present in your digital data. It is not present in the input signal. Aliasing is an artifact of sampling and totally contingent upon sampling frequency. So your sampling frequency is going to be important, your Nyquist frequency is going to be important, your signal frequency is going to be important, because you need to know the difference between your signal frequency and the Nyquist frequency to be able to predict where the alias sine wave will occur in frequency. Okay, let me do just one more thing to convince you that that 8 megahertz is an aliased signal. I'm going to change the sampling frequency from 20 megahertz to 40 megahertz. So I'm going to increase the sampling frequency, which increases the folding frequency as well. So I'm going to go from 20 megahertz and turn the horizontal knob clockwise, and you can see it's now 40 megahertz is your sampling frequency. And notice that the 8 megahertz signal is gone, and now it's back at 12 megahertz where it belongs, which is actually the setting on the function generator that I have right now. Okay, so it's this 12 megahertz that gets folded back when you sample at a 20 megahertz sample rate and ends up at 8 megahertz. Okay, I will leave you to the lab, and you will do exactly the same thing for a different frequency.